thanks to the organizers for making this happen, for inviting me. So the first time I think I visited Lumini was around 91. Probably most people just attended the kindergarten at that time, most people here. So I'm an experienced one, so it is probably my 6th or 7th visit to this place. It's always nice, very beautiful and relaxing place to be. With very good mathematics going on, always. Okay, so that's what I would like to talk about today. It will be kind of an overview to some extent of this subject of what conformal measures are, how they play out in holomorphic, in various branches of holomorphic dynamics, with some very classical stuff that I will start with, like one-dimensional rational maps. So that will be our entrance point. And then we will move on to natural extensions of these rational maps, which is some intermediate step between rational maps in dimension 1 and so holomorphic maps in dimension 2, in particular Henon maps. And I will discuss how these objects play out in this area. So somehow they have not been much emphasized in two-dimensional dynamics, but I think that it is very interesting object to pay attention to, and so I would like to, it's one of the messages that I would like to convey, just to pay bigger attention to this kind of objects. And another direction, parallel direction, is towards the groups. So from one-dimensional rational maps, we will pass to the groups, which was actually the origin of the idea of conformal measures. And then I will say a few words in the direction of higher rank actions. It's some ongoing projects. So there will be some very classical stuff and some ongoing projects that I will just tell a few words about. Okay, so let us try. Yeah, so a couple of the two messages that I will try to convey is that somehow along with the measure of maximal entropy and associated currents that people love here in this room, one can pay bigger attention to this kind of geometric measures and currents. And also, I would like to emphasize the method. So the geometric method of constructing, soft geometric method of constructing these objects, which is called Patterson-Sullivan method, which is very easy to apply and potentially can be applied to a very broad class of situations. Okay, so let us move on. So what is conformal measures in the setting of polynomials? So more general, one can talk about rational functions in one variable. So let us consider polynomial in one variable, very familiar object, I think, to everybody here. So we have a basin of infinity. So d of infinity, we have the boundary of this basin of infinity, which is the Julia set. And we would like, this is the set where the dynamics is chaotic. And in order to control the chaotic dynamics, we usually apply the methods of ergodic theory. We put some natural measures on this set and try to understand typical behavior of orbits with respect to this measure and geometric properties of this measure. And so, and along with the measure of maximal entropy, there is another very natural and in some way geometrically even more natural measure, which is called conformal. And it is defined as not invariant, it is quasi-invariant measure, so let us call it nu. So a quasi-invariant measure is called conformal if it is transformed by the power of the derivative of the map. So that is the definition, that one can define the Radon-Nikodym Jacobian of our measure nu. So it is done by pulling back this measure. So the natural operation on measures, as we know, is push forward, but still one can pull back the measure by spreading around homogeneously discrete measure on the pre-images and then averaging. This will be pulled back and then taking Radon-Nikodym derivative with respect to the original quasi-invariant measure. That is the Radon-Nikodym Jacobian, can be defined in a very general way, like that, for any quasi-invariant measure. And if it happens that it is some delta power of the derivative, then the measure is called delta conformal. Well, so the equivalent definition would be sort of maybe more specific way of saying that we take some measurable set X on which the map is injective, and then the measure of the image of this set should be the integral of the power of the derivative over the set. That is equivalent definition of the conformal measure. Okay. Well, actually, let me emphasize right away that conceptually, one should think of this not as just individual measure, because we have in the definition, we have the norm of the derivative, and norm of the derivative depends on the metric. So the definition of the measure depends on the metric. So, and there is a very nice way thinking about that. I think going back to Dennis Sullivan, one should think of this as associating to any metric in a conformal class. So for instance, the conformal class of the spherical metric on the Riemann sphere, one can associate a measure nu sub rho, such that, so if the metric changes with the density, with this density, that the measure will change with the delta power of this density. So somehow we sometimes use for this kind of object a term stream, though it is not broadly used, but I may use it in the future to emphasize, in this talk, to emphasize that it is not actually one measure, but a class of measures depending on the class of conformal metrics.
Does the existence of such a stream equivalent to the existence of conformal measure?
Yes, so you take just some measure and then you transform all other measures according to this rule. It is
yeah, but on the other direction, you start with this, you have a conformal.
Well, if we associate, so yes, it is the same, yes, it is good. Yes, it is a less trivial question, yes, but it's the same. What? So delta, exponent, yes, it's some delta. The measure is called in principle, for different delta could be different, correspond different conformal measures. So, yeah, so somehow it happens that under many circumstances, this delta is uniquely defined, so, but it is not obvious that it is so. Okay, I somehow still a little bit confused what is forward and what is backward here. Okay, so now an important class of polynomials in one variable is hyperbolic polynomials. So one of the definitions is that it is uniformly exponentially expanding on the Julia set. So here is this property of uniform exponential expansion. Another property is that there are finitely many attracting cycles which attract the whole complement of the, and which attract all the critical points and all the complement as a consequence of the complement of the Julia set. So it is a very well studied, very simple, and very important class of maps, and somehow today I will focus mostly on that. So the goal is potentially to go beyond this class of maps, but today hyperbolicity would be usually my standard assumption. And there is a classical theorem from the 80s, I think, by Bowen and Sullivan, that for any hyperbolic polynomial in one variable, there exists a unique conformal measure. In particular, the exponent of this measure is well defined, unique conformal measure. The exponent is nothing but the Hausdorff dimension of the Julia set. The measure is ergodic, and moreover, there exists unique invariant measure in the measure class of this one, absolutely continuous with respect to this one, invariant measure. So as I thought, this conformal measure nu is quasi-invariant, but will, like invariant measures more, ergodic theory is nicely plays out for invariant measures. So it's nice to have an invariant measure in this measure class, and these measures are called Gibbs measures. The reason for this name comes from the fact that these measures can be constructed so by means of by methods of thermodynamical formalism. It is a simple consequence of the powerful techniques which is called thermodynamical formalisms, Some people in the room, well, in dynamics, all people in the room are well familiar with these techniques, which allows us to produce for various potentials, to produce various natural, quasi-invariant and invariant measures. Very powerful, but there are downsides for these techniques, so it is difficult to apply beyond the hyperbolic setting. In the hyperbolic setting, it works perfectly well. Beyond hyperbolic setting, there are problems. That is why people usually, when they go beyond hyperbolic maps, they try to use more direct geometric methods. Okay, so and in particular, so one can apply this Patterson-Sullivan method. So Patterson introduced it in the context of Fuchsian groups. It is in the 80s, maybe late 70s even. Then Sullivan generalized to all Kleinian groups and then pushed it forward to dynamical setting. So, and it is based on the notion of the Poincare series. I did not put it on the slide, but this series, which is written here, so as a function of S, it is of exponent S, it's called the Poincare series for our rational map. So what do we do here? We take some base point, Z0, and we take all preimages of this, n-fold preimages of this base point, and then we sum up the derivatives in these preimages of n-fold iterate to the power S, and then sum up for all preimages. So it is big series, so for over all preimages of a base point. And then one asks the question, so when there is a power series, of course, the first question to ask whether the series is convergent or divergent. So, and it happens for simple reasons that this series is convergent for sufficiently big S, for some S bigger than some power, some exponent delta critical exponent, and they're divergent for small power, for small exponents, smaller than this delta critical. So at the delta critical, in the hyperbolic case, the series is divergent. This case is called divergent case. But in the critical exponent itself, both cases can happen. The series can diverge or converge. The easiest case is divergent, and in the hyperbolic case, that's exactly what happens. And in this case, one can construct a conformal measure. So by, in this very soft way, just take S sufficiently big, bigger than the delta critical, take S bigger than the delta critical. So put in the n-fold preimages delta masses, so with these weights, which appear exactly the weights that appear in the Poincare series. So and sum up, so it is some finite measure because the series is convergent. Normalize it by the Poincare series, we obtain a probability measure, and then pass to a limit along the subsequence when it converges from above to the critical exponent. And it turns out that actually it does not depend on the subsequence, at least in the hyperbolic case, and it is a conformal, the conformal measure that I defined on the previous slide in the hyperbolic case, introduced in the hyperbolic case. But you see, this is absolutely soft method. So absolutely soft, nothing, not much is needed here. Here is the construction, and it actually works for any rational functions. So, or at least for rational functions. Exactly like that, it works for rational functions for which the Julia set is not the whole sphere. So otherwise it should be somehow modified. So, but again, yeah, we will keep in mind that non-hyperbolic case is our maybe potential goal for some other Lumini conference, but today we are focusing on the hyperbolic case. So, well, so thermodynamical formalism in the hyperbolic case tells us that if we just equidistribute the mass with these weights, inverse of the powers of the derivatives. Oops. So let me see. If we equidistribute these masses along for n-fold pre-images, equidistribute these measures, normalize appropriately, then we will converge to the conformal measure. That is the outcome of the thermodynamical formalism. However, in the context of the Patterson-Sullivan ideas, so we can consider weaker notion of equidistribution. We can understand equidistribution in the sense of Poincare series. Just take the Poincare series for exponent greater than the critical one. So consider the corresponding finite measure, normalize, and if it converges to some nu, then we will say that pre-images of points, weighted pre-images of points are equidistributed in this sense. It is some average. This notion is certainly a stronger notion, and it is some kind of averaging version of this strong equidistribution. So I sort of I refer to it as PS equidistribution, Patterson-Sullivan equidistribution. Okay, so that would be one of our questions, running questions today, whether the points and more generally some holomorphic curves, or maybe manifolds of high degree dimensions, or whether they are equidistributed to some limiting objects in this sense. Okay, so let me try to move forward. Okay, that is as much as I wanted to say about dimension 1, which is the model case for everything. For dimension 1, one-dimensional holomorphic dynamics of rational maps. And now we can make a half step forward, namely consider the natural extension of the, or inverse limit sometimes called, of this rational map. So it is just the space of inverse orbits. So you take some point z0, take this pre-image, then take another pre-image and move forward to infinity. That is the inverse backward orbit. So inverse orbit or backward orbit, sorry, for our map, and we consider the space of these inverse orbits or backward orbits. So this space naturally projected to the complex plane, just to the first coordinate. Projection is to the first coordinate, and there is also dynamics, natural dynamics. It is just point coordinate-wise, component-wise dynamics of the map F. Produces the dynamics lift of the F, lift of F to the natural extension, which will be denoted F hat. Or you can think of this as you just apply F to the first coordinate. You keep all these coordinates the same, and then apply F to the first coordinates. This is our action of dynamics, and then this dynamics becomes invertible because the inverse map is just forgetting this first coordinate. So the point of this construction, somehow original point, it is general construction from ergodic theorem, even from algebra if you want, so is to turn non-invertible map into invertible maps. Just lift it to invertible maps. Okay, so but in our situation when we deal with holomorphic dynamics on the complex plane, there are very nice geometric properties of this lift of the natural extension. Now, first of all, essentially by construction, is it's a counter-fibration. So over the complex plane with finitely many punctures. So namely we have to puncture out the attracting cycles. We are in the hyperbolic situation again. So again, it can be done, many things that I'm talking about can be done in more bigger generality, but I restrict myself to the hyperbolic situation. So there are finitely many attracting cycles that govern all the dynamics. So we puncture out these attracting cycles, and on the complement of these finitely many punches, it is a locally trivial counter-fibration. So, well, the pre-images of points are always counter sets, but it is a fibration outside of these finitely many points. It's a kind of vertical fibers. We think of this as a vertical fibers of our natural extension. But what is even more interesting, so it is kind of immediate. What is more interesting is that it has a horizontal structure, a nice geometric horizontal structure. Namely, it is a C lamination. So it is an object which locally looks like a sort of domain on the complex plane times a counter set. And the transition maps from one such flow box to another flow box is horizontally conformal. So that is what is, and moreover, the leaves, there are global leaves of this lamination, and these leaves are complex planes. So it is Riemann surfaces, sometimes say Riemann surface lamination with leaves which are complex planes, complex lines. So, and again, we should punch out finitely many points. Namely, we have to punch out the periodic orbits which are lifts of the attracting periodic orbits on the complex plane. And outside of this finitely many orbits, there is this nice laminar structure.
Excuse me, Misha, you say super attracting is attracting, right?
It's attracting. I said super, sorry.
It's written super.
It is super, it is written, oh, there is a proof. So outside of super attracting cycles, yes. So do we have an eraser? Yes, sorry, yeah, it is attracting. I used to think of simplest examples as a point is super attracting. And okay. Well, so the dynamics, if the map is hyperbolic, then the lifted map f hat is also hyperbolic on the lift of the Julia set. And these vibrations and these lifts play the role of the stable manifolds and unstable manifolds. So the fibers are a kind of semi-local stable manifolds. It is not full stable manifolds. To take full stable manifolds, you should take the fibers over all the preimages of the point. They're kind of disconnected. They're disconnected anyway, so they're counter sets. But in so more a stronger way they're disconnected. And the leaves, this complex plane, are unstable manifolds of our dynamics. So we have this hyperbolic dynamics with this structure, with this nice structure. So, and for this hyperbolic dynamics, we can construct the not only the leapwise measure on this, not only horizontal measure, we can construct transverse measure on the fibers. And so it is measure on all the fibers, on every fiber, and the measures will be, well, no, over the Julia set, I don't know over all, I should, well, the measure on the fibers, so in the measure theoretic sense, all the fibers don't make much sense. But well, I guess it makes sense in this case. So it is measured on all the fibers, which is transformed in this way. So if you go from one fiber to another fiber, so there is a contraction, and the Radon-Nikodym Jacobian of this contraction, Radon-Nikodym Jacobian of this contraction will be the derivative to the power negative delta. The norm of the derivative to the power negative delta. So it is just this conformal property on the fibers, but because it is stable manifolds, we have the inverse power of delta. And also it is kind of important what happens under the holonomies. So we have somehow two dynamical systems here. We have the dynamics of f hat, and we have holonomy when we take a flow box. We take a flow box, we take two transversals, and we go from one transversal to another transversal along the leaves. It is our holonomy maps. And for these holonomy maps, we can write explicitly as well the Radon-Nikodym derivative for the, well, when we pass from one fiber to another fiber, as the power of the Anosov-Sinai cocycle. This Anosov-Sinai cocycle is obtained in the following way. Take 2 points, so this point and this point, on our leaf, start to take the inverse preimages. They get together exponentially fast. We are on the unstable manifold. They get together exponentially fast and measure the ratio of the derivatives at the corresponding preimages. So again, I did something wrong. Measure the ratio. So this product, because they get together exponentially fast, this infinite product is convergent. And so it makes sense, and it is what is called the Anosov-Sinai cocycle. And the delta power of this Anosov-Sinai cocycle is the Radon-Nikodym derivative of the holonomy map. So there are these two transformation rules for our conformal current. So, and construction of this can be done. So, well, again, in the hyperbolic case, one can do this in various ways, but it can be done by the in the soft Patterson-Sullivan way, just putting. So we will decompose the fiber by the images of other fibers. So just take the fibers over the inverse pre-images of this point, take the push forward, and so it will. So these guys will be inside of our fiber, and put the corresponding masses on these sets, and then turn on the Patterson-Sullivan machinery. Write down the Poincare series, so define its critical exponent, and consider the corresponding masses and the limit of the corresponding masses, and this would produce for you conformal measure. Actually, here. So again, let me say that it is defined on all fibers, and there is this transformation, these two transformation rules. So we have constructed this transverse measure to our C lamination, transverse conformal measure to our C lamination. So this measure is not holonomy invariant, but it is transformed in a very specific way, geometric way, so governed by the Sinai-Anosov cocycle. Well, one can also consider a leaf-wise conformal measure. So the simplest way of doing that is just to taking the conformal measure downstairs that we know and just lift it to the leaves of our lamination. Yeah, so you can use, so if you use a pullback measure, you can literally lift, but maybe it is not the best way because pullback measure has singularities. So you can first use the pullback measure and then transform to some nicer, so conformal measure on our lamination. So, and in this way, you will construct the leaf-wise conformal measures, which are transformed also in natural ways, natural conformal ways under dynamics. So, and yes, so that is this transformation rule. If we pull back, just this transformation rule is inherited from downstairs. So we have conformal, transverse conformal measure, which is transformed by the Jacobian to the power negative delta. We have leaf-wise conformal measure, which is transformed by the Jacobian to the power delta. When we pair these measures, we take the product of these measures, and so we will get an invariant measure. That is how one can construct in a geometric way an invariant measure which is conformal in the leaf-wise direction and conformal in the transverse direction. So, but we kind of split these two procedures. First transformal, then we take care of leaf-wise direction, and then the product will be an invariant measure. So this is something that came out from our old work with Vadim Kaymanovich. So, yeah, so that is, on the natural extension we have this thing. But also, I would like to add a little bit to this discussion, which I think that I kind of put these formulas first time. So it is some interpretation in terms of the currents. So not only measures, but in terms of the currents. Namely, when we have this transverse measure, it is tempting, of course, to define a certain current associated with this measure. And here how we can do this. So take a test form, and then integrate this test form over the leaves. So take a flow box. Here is a flow box. Let's say test form is supported on this flow box. We integrate over the leaf with density, which is Anosov Sinai cocycle to the power delta, and then integrate over the base fiber. So you select a base fiber. So this is a transverse measure over this base fiber. This is Anosov Sinai cocycle from this base fiber to another fiber. So, and so we can write down correctly this kind of conformal U current. So 1 current on our lamination. And then we can kind of say that the leaves, so the leaves of our lamination under the dynamics are equidistributed, weighted leaves are equidistributed with respect to this current. So if we push forward, take some unstable leaf, push it forward, so weight with appropriate weights. So now we are dealing with the geometric conformal currents. We need to use these weights all over again, weight with appropriate weights. This will be our current of integration. Normalized appropriately, it will converge to this conformal current. So we can start with current, with a conformal current, rather than immediately going all the way to the measure. So again, conformal U current now. So yeah, that is all. That is all, I think. For natural extension, that is all. So the upshot for the natural extension, that so we have we have the transverse conformal measure, we have leapwise conformal measure, we can pair them to obtain an invariant measure, and we also use the transverse conformal measure as the basis for constructing a conformal unstable current, and the leaves of our lamination, unstable leaves of our lamination, will be equidistributed with respect to this current. Okay. The current is not harmonic. It's not harmonic. It is related to harmonic current. In our discussion with Vadim, we lifted this current to three-dimensional lamination, and then it is lifted to three-dimensional lamination as harmonic. But this one, it's conformal. It's conformal. Exactly, which is not harmonic. It's not harmonic, yeah. Okay, but it is a very good question because it is deeply connected to harmonic currents. Our goal, actually, main goal was to construct harmonic current for this hyperbolic three lamination. So, and that was a tool to do that. Okay. Okay, so there is a picture for complex Henon map. So that's formula for complex Henon map. And so we will consider somehow dissipative case, just because I like dissipative case. So a lot of what I will say may looks actually even better. Some looks even better in the conservative case, and I think that everything comes through, so there is no much differences. But for definiteness, let us consider dissipative case. And so we have these various versions, forward and backward versions of the basins of infinity and Julia sets. We have a forward basin of infinity. In my picture, it is schematically here. We have the Julia set, which is the forward Julia set J plus, which is schematically here, which is the boundary of the forward basis. And we have backward basin to infinity, and the backward Julia set J minus, which is in the dissipative case looks like elimination. So it's not elimination, but one can safely think of this as some kind of measurable lamination, not topological, not uniform, but some kind of measurable lamination. So, and we intersect this forward Julia set, we can intersect forward Julia set with a backward Julia set, and we obtain this Julia set J. So there are three versions of the Julia set, and the chaotic dynamics happens on J. Chaotic dynamics happens on J. So, okay, so the conformal measures were considered first probably by Alberto Verkhovsky, his young collaborator at the time, Jan Wu, in the 90s. And so they proved that there exists stable and unstable. There is measures, so there is S and U invariant measures, mu, which are absolutely continuous to the Hausdorff measures on the stable and unstable foliations, respectively. So if we consider these measures, so if we disintegrate these measures along the stable and unstable foliations, then we will obtain something which is absolutely continuous with respect to Hausdorff measures. In particular, Hausdorff measures will be finite on the stable and unstable foliations. So both these measures are ergodic, and here I should say that the stable direction, stable Hausdorff direction of one measure and unstable Hausdorff dimension of the other, so sum up to the full Hausdorff dimension of the Julia set. So that is the result, and of course they also applied the methods of the thermodynamical formalism, so because it is hyperbolic situation, so standing assumption is a hyperbolic situation. Okay, then Christian Wolff so moved on, so just and showed that if we want to construct an invariant measure of maximal dimension of in the so which is equivalent to the full Hausdorff dimension, so those measures that appeared on the previous slide, they are equivalent to Hausdorff dimension in the stable and unstable foliation. But if we want a measure which is equivalent, invariant measure, which is equivalent to Hausdorff measure on the full Julia set in the right Hausdorff dimension, then it is difficult. So these measures exist. So if and only if the conformal measures they constructed is the measure of maximal entropy. And for this one needs to have all exponents of all characteristic exponents of periodic points to be equivalent. It's very strong restriction. So the conjecture was that maybe it never happened. So in rational situations there are very special maps like Chebyshev maps for which this kind of situations happen. But Chebyshev-Latter. So in the Henon case, suspicion was that it would never happen, and actually very recently by Romain Dujardin and Serge Cantat, it was shown that indeed it almost never happens. So if the Julia set is not Cantor set, is not totally disconnected, then it cannot happen. It cannot happen. So the case of the Cantor Julia set remains open, but still in most cases there is no invariant measure of maximal Hausdorff dimension. So it is kind of unpleasant, but in some way it can be, it is fixable to some extent, and that is what we have done in our ongoing project with Christophe Dupont and Alyona Yurchenko. So we have added to that picture that actually there is a quasi-invariant measure in the right Hausdorff dimension. We can kind of pair our unstable invariant measure and stable unstable conformal measures with stable conformal measures. Think of this as just foliated measures. So we can pair them and to construct a measure which is not invariant, but it will be a quasi-invariant measure which will be absolutely equivalent to the Hausdorff measure in the right dimension. And moreover, so this measure is a kind of like Lebesgue measure in the case when the Julia set is not the whole manifold, but it is some fractal set. So this quasi-invariant measure. And for in this kind of situation, people in dynamics ask for the forward and backward SRB measures for how the orbits of such a quasi-invariant measure equidistributed with respect to whether they equidistributed with respect to some natural invariant measures. And indeed, that is the natural situation. So if we take a typical point for our quasi-invariant measure, typical point Z for our quasi-invariant measure, and we take Birkhoff averages of our point, of the orbit of this point, then in the forward time, they will converge to this unstable conformal measure, and in the backward time, they converge to the stable conformal measure. So it is very reminiscent, so it is exact analog, actually, of the usual SRB picture for Anosov maps. So the role of this quasi-invariant measure is just the Lebesgue measure, and there is usually no absolutely continuous invariant measure, but there is a forward Gibbs measure, backward Gibbs measure, and they give the forward and backward asymptotical distribution of the orbits of our system. So yes, it is ergodic, yes. Yeah, it is actually not completely trivial statement, but it is one of our lemmas that the measure is ergodic. Okay, and again, we can somehow make the step backwards and start to construct this gradually. So to construct first transversal conformal measures and leafwise conformal measures, and to start to produce various objects out of this. Okay, so here is the statement, here is the construction of the foliated transverse invariant measure. So we consider here the unstable foliation, so U, so that is our unstable foliation, and so we consider the transverse measure on the stable leaves. And so the claim that there exists such a measure, unique, so and which satisfies the transformation rules. So there exist transformation rules. So under the dynamics, it is transformed by the power. Under the dynamics, it is transformed under the power of the derivative, and under holonomy, it is transformed as the power of the Anosov-Sinai cocycle, which is defined exactly as in the natural extension. The picture is the formulas here is exactly like for the natural extension, and we can, out of this transverse measure, we can produce a transverse current, which will be also transformed as a conformal, not transverse current, but conformal current, which is transformed in a natural way. So we can repeat the picture that I have just outlined a few minutes ago for the natural extension. Natural extension is a good prototype for the Henon map. So we have the same objects, but in the Henon situation we have more. Here we have only unstable picture. In the natural extension we have only unstable picture. Here we have also stable picture, but maybe I should, before going to the stable picture, to complete the unstable picture, then there is a statement about equidistribution of the unstable manifolds. Exactly the same formulation as for the natural extension. You take the images of some piece of the unstable foliation, weight them with appropriate weights, and pass to a limit in the sense of, say, Patterson-Sullivan, or one can do this in a stronger sense, and they will equidistribute it with respect to this current, with respect to this unstable conformal current. So it is the same picture. So that is what is nice about natural extension. Somehow people neglect it a little bit. I would advise people who are doing Henon maps always pay attention to the natural extension. It's a good prototype case. Okay, but we can also construct the transverse stable current, just replacing unstable direction with a stable direction. We can construct the transverse stable current. And we can also construct two more currents. There are 4 currents here. We can also construct the corresponding leaf-wise currents. So in the construction of the unstable currents, U currents, we used the unstable derivative. In the construction of the stable current, we use the stable derivative. And and we can do this on the leaves, and we can do this on the transversal. So we have obtained 4 objects, and then we can pair these objects in a various way. So if we pair the unstable transverse and leafwise currents, then we obtained the Vilhovsky-Wu conformal measure mu u. If we pair stable currents, we obtain the corresponding conformal measure mu s. And if we pair unstable leafwise current with stable leafwise current, then we obtain the quasi-invariant measure of full dimension that I just described in the previous slide. So that is kind of, I think that from the point of view of the people in high dimensional dynamics, it is a kind of natural way of doing that. So starting with currents and then trying to wedge these currents to produce various measures. Of course, beyond the hyperbolic situation, there is an issue of justifying these wedge products. And, well, some issues in justifying of the existence of currents as well, but probably this issue is not so serious. But it is a kind of something that we are now exploring with Christoph and Alena.
There's one product missing here.
Yeah, I don't know what I will get because it is very strange. So, for instance, yeah, it is Ronsin. So we have leaf-wise. We use yeah. So this produces conformal measure on the leaves. This on the unstable leaves. This produces conformal measures on the stable leaves, and so we wedge them. And here we use transversals, but we use derivative in the transverse direction. So we use transversal. So if it takes the dual sin, and I don't know what it will do. So it's a very good question. Probably I should give a better thought to it. Maybe there is something interesting. Okay, yeah. I just wrote all these formulas especially for this talk just 2 days ago, or 1 week ago. So not everything is in place yet. Okay, now let us go to the group situation. So if we take a classical Kleinian group situation, so a discrete group of Möbius transformations of the sphere. So we have, instead of Julia set, we have the limit set. And our assumption for today, standing assumption for today, will be that the group is convex or compact and non-elementary. And convex or compactness is exactly equivalent of the expanding property on the Julia set, so which is formulated this way. So it is an analog of expanding Julia sets. And then one can construct this classical theory, Poincare series, which was first, but exactly in this context, was written by Patterson first. So take some base point. So from the three-dimensional point of view, you take some base point in the hyperbolic space, Q, take the orbit of this base point, measure the distance, and write down this series. And then you have a critical exponent and turn on the whole this machinery of constructing the measure, Patterson-Sullivan machinery, and you produce a conformal measure at the sphere at infinity. And it will be conformal with respect to the visual metric associated to this base point Q. There is a base point Q involved here. This will be a visual metric. If we change the base point, then the visual metric will change, and the conformal measure will change accordingly with the rules of the conformal stream, with this delta transformation rules. So yeah, so here is one can use also the construction right on the Riemann sphere using these derivatives, Poincare series in similar to what I have written for the rational maps. And there is actually, under some circumstances, there is a very explicit connection between rational maps and groups. For instance, if you take a Schottky group, so which maps this circle, so there are two generators here. This circle goes to that circle under one generator, this circle goes to that one under another one, and you produce a map, defined piecewise Möbius map, defined on the union of these four disks, so which is here one generator, here it is inverse of this generator, here it is second generator, here it is inverse of the second generator, so it is piecewise map, and you turn on the machinery of the maps, conformal measures of the maps, and it will give you exactly the same answer as for the groups. So in this case, this map is sometimes called Nielsen map associated with this group. It contains the whole information needed for understanding the group. Sometimes it is called Bowen series map, who studied it in the 80s with a reference to some original ideas from Nielsen. Okay, so that is groups. That is a Kleinian group situation. So let us see, have I skipped something? No, I'm done with classical Kleinian groups. So, and let me just spend a few last minutes saying a few words about our ongoing project, work in progress with Buck Dunk, Misha Kapovich, and Shenyuan Zhao. So we are trying to see whether one can make this kind of ideas work for higher rank actions and motivated by possible dictionary between higher rank actions and higher dimensional dynamics. So in high-dimensional dynamics, currents play a big role, and so we started to ask questions about currents in the some high-rank actions. And I will just, so well, that is kind of one can think in some very general way. So you have some algebraic action on some algebraic variety, and take some subvariety and start to average this in the sense of Poincare series, start to average, so take the orbit of this subvariety under our group action, average in the sense of Poincare series. Here is this average. So here there is some length function. It is a function of the length of our element. So it can be some geometric nature function or just length itself. And then you consider the current of integration over the push forward varieties. And so you write down this series, you write it for the sufficiently big exponents, bigger than delta critical, normalize by the Poincare series, and try to pass to a limit and ask what you will get. So that is the question that we have asked, and let me show how it plays out in two simplest examples. Two simplest examples. So first example, it is just a Kleinian group, one-dimensional Kleinian group, just product action. So it acts so in the same way on two copies of C, on the product of C. It is just a product on each coordinate, it acts in the same way. So that is our action. So take some holomorphic curve, sigma in this C2. So let us decompose it. So let A and B the homological coefficients of the class of sigma in two-dimensional homology. So that is its decomposition along the horizontal and vertical fibers. So, and then we can push forward as described on the previous slide. Consider this Poincare series, average along this Poincare, average in this way. And so everything will converge to the combination of two laminar currents. So one of them will be current of integration over horizontal leaves, where the transverse measure is the conformal measure for our Kleinian group. It is classical Kleinian group for which we know what conformal measure is, and we just take this as a transverse measure to the horizontal current and the transverse measure for the vertical current. And that is our combination. So the orbit of our curve will converge. So will be equidistributed with to the combination of these horizontal and vertical currents, conformal currents, with coefficients A and B, which is exactly these original coefficients associated to the sigma. So the answer will depend on the sigma, on the homological position of the sigma. So, and actually the picture is very simple. So here is our product. So take one element, just let us think of one element of our group. It's some hyperbolic element with a repelling point, attracting point, and two saddles. And here is our curve sigma going like that. And so let us consider the intersections of our curve sigma with the vertical fiber, And when we start to push it forward, so there are these A intersections with the vertical fiber. When we start to push it forward, then it will start to, because it is a saddle point by the dynamical lambda lemma or by inclination lemma. So this fiber will start to stretch along this stable manifold of the along this horizontal lip through the attracting point. So, and if we start to average that, then we will obtain, in the limit, we will obtain exactly this vertical fibration with the transverse conformal measure. And similarly in the other direction. So horizontal fibration with respect to the transversal measure. So, and similar picture is for the other part of our curve. Somehow we take these vertical intersections, we will start to stretch along these vertical fibers. Horizontal intersections will start to stretch along the, well, horizontal intersections will start to stretch along the vertical fiber, and when we average, they combine together exactly to what was written on the previous slide. So it is kind of intuitively very believable, easy to understand. There are a couple of technical issues here. One technical issue that the picture does not quite work near the repelling point because the dynamics is not hyperbolic here, but conformal, and there is no such kind of stretching, but it will not contribute much. This part of the curve which is near repelling point, which will give only a small contribution to the answer. And there is another, maybe more important issue, is non-uniformity of this Morse-Male structure. So it is individual element, and we somehow, in order to justify this for the whole group, we need some uniform control for this kind of Morse-Male structure. So which is lost if the attracting and repelling points are close, and it happens for some elements. But people in the group theory, in particular Misha Kapovich, prepared for us a needed tool, which they call redressing theory, which allow to twist our elements of the group, by finitely many elements which are a priori, which can be selected a priori. So to get these points separated, and that after this twisting, one can somehow justify this picture correctly. Okay, just a couple of minutes for the last slide, which is not the last slide, but the last example, the last topic. It is this one more example, the second simplest example that we considered. It is a flag manifold. So in C3. So it is, oops, sorry. Yes, here it is. So flag manifold in C3, so it is, one can think of this as just pointed lines in P2. So line and a point, line L and a point P on this line in the projective space. And then we have two projections from this flag manifold. It's three-dimensional manifold. It's projected in two ways to the P2. So it is projection to points, it is projection to lines, dual projection. So, and we have two fibrations. Accordingly, we have two fibrations, line bundles. So one line bundle and another line bundle. So the fibers of these bundles are indicated here. Fibers of the first bundle are just pencils of lines. Fiber of the second bundle is a line on which all the points are marked. It is so-called two-dimensional Schubert cells, which represents the basis in the second homology of our flag manifold. Okay. So, and we considered some, first we considered some very simplest action that people know. It is so-called Veronese action. So related to a representation of the group SL2C, so reducible to the irreducible representation of SL2C and SL3C. And for this representation, there is an invariant curve. So the image of P1 given in this explicit way. So it is a curve, holomorphic curve, algebraic curve in P2, conic. Actually, conic in P2, it is just one orbit of our representation. And so by kind of more or less from constructions of this related to this representation, it turns out that this curve is invariant with respect to SL2C actions. There is a conic in P2, which is invariant by the SL2C action. And then this conic can be lifted to the flag manifold. Let us call this conic V. It is in P2. This conic can be lifted to the flag manifold by taking tangent lines. So just any point here is lifted to the tangent line pointed at this point. So it is a lift of our conic to the flag manifold, and in this way we will obtain a Kleinian group. So acting, so SL2C, so acting on So on the flag manifold, keeping invariant this algebraic curve. Okay, so that is the Veronese action. So what is? So it is still some not completely higher rank action. So we have high dimensional space, but we have just classical Kleinian groups. We know well what is Poincare series for this classical Kleinian group. So we want to take just this classical Poincare series, apply to holomorphic curves, sigma, and to see what will happen. And the answer will be the same, very similar to the product case. The product case, as simple as it is, so is a good model for much more general situation. So we can consider the position of this curve in the second homology, so decompose it over these Schubert cells, which I described, fibers of these two projections, coefficients A and B. Oops. So let me see. Fibers A and B. And then when we do the Patterson-Sullivan averaging, then we will converge to two foliated currents, with exactly these coefficients A and B. One of them will be foliated by the fibers of one fibration, another one will be foliated by the fibers of the other fibration. And finally, the last slide. And it is related also to the picture of just a single map in our group, a single map. So it acts in P2. It is a triangle in P2. It is 3 fixed points in P2. So repelling, attracting, and saddle point. And they live to 6 fixed points. They live to 6 fixed points in the flag manifold. So various indices indicated here. So one repelling, one attracting, and 4 saddle points. And so here is two-dimensional. So we take 2 saddle points here, say, that is the stable manifolds. And if that is the unstable manifolds, which are the Schubert cells. And if we take a manifold, take a curve crossing this unstable manifold, we count the intersection points, there will be A of them. And if we push it forward, they will start to stretch over these Schubert cells. So, and it exactly will lead to the answer that was written, which is, and it can be actually justified with a similar tools as I have mentioned. Similar difficulties arise, and similar tools can be applied. And actually, the ongoing project, it can be done actually in very general situation of general flag manifolds. So these kind of ideas can be pushed quite far. Okay, thank you.
Okay, some questions from Misha?
Yes.
So in many settings you use the...
In which setting?
In several settings you use the standard metric on the Riemann sphere.
Yeah.
But this metric is not unique.
Yes, so well, if the metric is changed, then that everything will be transformed accordingly. Yeah. What will not change is invariant measures. Invariant measures are unique because you pair, right. And so everything will lead to the same object. But conformal measures, quasi-invariant measures, everything will change. Yeah. It will be metric dependent. It's very important. So very important point to think exactly as functional from metrics to measures rather than just one measure. Thank you.